Okay, I'm here doing a sound test before I get going. My name is Bob Grenier. I'm a volunteer with Martin Fleischmann Memorial Project. So hopefully you can hear me today, and hopefully I don't sound like I'm Barry White, but that may still be the case. And hopefully there's no echo, so I'm going to test the various ones. Okay, Diodon, you're there first. So, do I sound like Barry White on this camera? Hi, Barry White, keeping you up all night. Okay, so, let me know. Can you hear me? Just a bit like Barry White? Oh no, how is that even possible? Okay, so can you still hear me on this? And I don't have any echo. Most importantly, hi David. Yes, can hear you. Can you hear me on this camera? Can you hear me on this one? And still sound like I've got a sinus cold. Oh no. Well, it's too important to get this information out. Okay, what about this camera? Can you hear me? Let me try and change the audio mic. I don't really want to do this. I really don't want to do this. Okay. Have I got a minute? No, we're running over, so I want to get going. Okay, so sounds good. Okay. All right, brilliant. My main priority here is that I have no echo. Okay, so it's been quite a long journey. I saw my first strange radiation when I was given some echo fuel in 2017 by Suhas Ralkar in India, in lieu of us being able to immediately test his reactor because I didn't have the equipment with me at that time. And so I took that back to here, the Czech Republic, and I put that next to the webcam that you can see me on here, but I covered it with a series of wraps of polytetrafluoroethylene tape, and then I exposed it for hundreds and hundreds of hours to the sample. And it took a long time to see some traces, but most importantly, we saw one of these squiggle traces, which was exactly the same morphology as structures that we later saw in the Ohmasa vibrator plates, and that was previously seen, but it wasn't aware at the time, by Takaaki Matsumoto. And this implied a kind of mesh-like structure, but also these kind of squiggles, if you can imagine them rolling along a piece of witness material, that would leave a kind of track to tread, but almost very similar to a crystal of, say, sand or some other crystal in a three-body interaction. And this left us with some challenges, but of course the webcam data stands on its own, and the fact that the morphology was essentially identical to that on the strange radiation track on the cupric oxide in the line reactor, and also the same kind of scale as other strange radiation tracks based off the size of the sensor, the number of pixels spanned. We knew exactly how big it was, so it was the right kind of scale for a typical quantize of strange radiation. We know it can't be a three-body interaction, and it has to have been neutral to have come out of the reaction fuel and through space and then ended up on the sensor of the Logitech 910C. So that was, for me, a watershed moment where I could start really considering these things as real. And it wasn't until a very special document by Bogdanovich et al. At the Moscow Institute, Nuclear Research Institute, where they were doing plasma flow discharges. So they had a water flow coming down, and they were doing discharges through to presumably an anode, high current, high short duration pulses. And they've been doing this, I think, since the late 90s, and they'd seen various what they called plasmoids floating about, and also string-like things that glowed floating about in their frames. But it was more recently that they published, I think it was in May 2019, or maybe even last year, but I think it was 2019. They published what I would consider a seminal paper in this field, which was where 2 days after they'd done this, they were observing on video structures moving around, seemingly toroidal-like, and emitting light on metal. And that is quite extraordinary, and does fit the data from Savatimova, and before her the work of John Hutchison, where it seemed that his materials were changing over time. And there are other people that have observed this since. One of them, I think, is Daviau, which we're going to talk about him tonight. The idea that this could persist for some time also is supported by the claims of Ken Shoulders, where he said it could stay in metals indefinitely and it could be excited into action. And that phrase reminded me of the 3-week-old nickel that had been exposed to hydrogen in the PN cell, I think in 1994, and that produced his and Foucault's highest excess heat. But when they got back from the nuclear authority, this little segment, 5-6 mil segment of this nickel rod, was emitting what he determined as a nuclear expert, protons at several MeV. And this implied that something was going on in the metal long after the exposure to the hydrogen. And then there was the 2004, I think, or maybe 2006 interview with American Anti-Gravity, where they interviewed S.V. Adamenko, Stanislav Adamenko, and he talked about things on the accretion plate that were able to absorb incoming ions and emit light, but you could not see the incoming ions or any secondary ions. So there was something left in that metal that was able to manipulate matter and convert it into light and or capture it. So these are some waypoints, but really it does start with John Hutchison and the investigation of John Hutchison's work by Ken Shoulders. And from there, it kind of snowballed. But for me, my journey started with a meeting in Budapest with Dr. George Eagley and discussing ball lightning. And that led me to a number of realizations and researching Ken Shoulders around that time. That was just coming into 2017, and then we had the strange radiation in the middle of that year, and what I called the lion track later. I think it was taken in September on the scanning electron microscope here at the Masaryk University. And so that, for me, was the most detailed strange radiation track, and it matched the kind of positional form that you get with these over a space, 3D space. And so it really, it's a shame that we never got to see the video from Bogdanovich, and maybe I could have pushed that harder, but he claimed to have video, and he said that these toroidal structures could form into crystal structures that he actually had a picture of, and they could move around spinning on their own axis, and the individual ones are spinning on their own axis, and then it could translate or roll across the surface. And this would be similar to my speculation that these kind of mesh-like structures that Matsumoto talked of from the early 1990s could be responsible for certain types of track. What was not really well explained is the large plethora of other styles of tracks which you can see in this field. And it wasn't really until I could understand that the material that is making these structures appears to be a coherent matter on the surface. Whatever that is, I don't know, but from the Lockheed Martin patent, which I first read in September last year, I learned something very key about coherent matter, and that is that most people take, say, sodium-23 ions down to, for instance, absolute zero, and that is you have the same matter, i.e. the same nuclei, at the same temperature, and then they're on a metal plate and they become coherent, and this makes a Bose-Einstein condensate type thing. And the key features actually were lost on me until I read that patent by Lockheed Martin for coherent matter waves. And what it is you need the same thing, be that a proton, the nucleus of protium, a deuteron, the nucleus of deuterium, monatomic in both cases, an electron. It doesn't actually matter according to their patent, and I would tend to agree with them, because you can make fermions by making Cooper pairs out of electrons, and you can obviously deuteron is a boson in its own right, but the key thing is to have the same thing to begin with, and then to raise it to exactly the same temperature. And in Solin's patent, he talked about electron bunching, and this was applied for, I think, in October 1992, following his research. And I think it was awarded in Russia. It's now past its protection, and so that's available for people to use. And he talked about electron bunching leading to coherence. And I believe that what we have demonstrated since late last year shows that what most people were achieving at near absolute zero, and what John Hutchison was achieving at room temperature by expanding on the work of Nikola Tesla, and what with the information from the Lockheed Martin patent, you combine those together, and it really means you just need the same thing at the same temperature and in phase. And the images that we shared early on, in fact the very first couple of videos in the VEGA experimental series, when I looked at them, what I thought I was seeing was something that was effectively, it's got a push inwards of the electrons and maybe ions, and it has a push outwards, and it has this very, very thin sheath where you could, I imagine, get this electron bunching process. In the Solin patent, what he used was a low vapor pressure metal, something like tungsten or zirconium or molybdenum, or those. It's in the patent. I've discussed that at length. But essentially, what it did is it had an electron beam coming into the metal, and the metal melted, and it then had a very hard boundary between the molten metal and the solid metal, and this produces a resonant cavity, and you get the electron bunching going on in there. And if it gets to coherence and it gets a bit more dynamic, it might melt a bit more and it comes away from the resonance and it comes back in. So it's self-regulating. In the case of Piantelli, and I discussed this at my in Q&A at ICCF 22, he told us that he had and it's not in the patent, but he had a high density winding at one end and then it opened out, and so he had a temperature gradient along the nickel rod. And what that meant is that if something was at the perfect resonance to create, in my view now, coherent matter, then that would be perfect for the materials in there, i.e. nickel and hydrogen at the size of nickel clusters, atomic numbers in nickel clusters that he had synthesized. And when that coherent matter is formed, and I will talk about how structures and holes, prominences and so on, in my view, can create that, but this work has already been done by another author. But anyway, it's in this particular zone. If that then gets excited and heats up, then it can move to a colder area if necessary, or a hotter area. So it has built-in parameter space sweeping. So you can, once it's going, it can keep going, even if it gets a little bit more excited and shifts up and down. So that was rather novel. But I think the key thing is to have a scenario where you can set up this electron bunching, or you can force a large amount of matter into a coherent state. And I've described how I was feeling by looking at the data. The first one was, I call it the tungsten chop shop. And what happened was the balls were getting to a state where they were excited to a point where they instantaneously cut the tungsten. So it basically went from being able to support a whole half ring of tungsten wire to almost instantaneously, in 1 or 2/30ths of a second, being cut, but only cut on the this very thin boundary layer. And so I believe that when the electrons are coherent, they form these highly magnetic structures that is then able to interact with electrons that are in a material, particularly in a conductor. And this causes a disruption of the metal. And as I argued and have shown, certain elements that are stable when they have all their electrons become unstable when you remove their electrons. And I talked about thorium 205, not thorium 205, thallium 205 going to lead 205 as a means to test this process. Now, if you have a sphere, and I'm arguing that these are equivalent to natural ball lightning, they're a technological equivalent to ball lightning, and I believe that the technological, the natural ball lightning is able to pull in air from its surrounding environment, and in the air it can, as it comes in, it can condense that matter, it can strip off the electrons. Often what you see when there's a Chinese study where they were looking with a spectrometer into lightning, and a ball lightning came into shot. So there, you can go and look at this on Wikipedia. And I talked about this in my Stanford presentation in early 2017, in January, I think, 2017. And what they showed was they observed silicon in there. Now, if you take two 14 nitrogens and you fuse them together, you get silicon. So, and that yields a lot of energy. So it could be trying to crush matter into a very small space. But the space in the case of a normal ball lightning is this coherent matter zone around the outside. Now, what is very clear from these kind of structures, they tend to form either spheres or toroids, but what has been shown by several authors now is that they can cluster together, and they have a like type ability, but if they push really close together, they're going to blend into each other. And in terms of natural ball lightning, I showed with a CMIT blog that in the Hessdalen ball lights, Hessdalen is an area in Norway which has very favourable geology. It has quartz in the ground, it has highly conducting metals in the ground, and you can imagine with freeze-thaw, I hypothesized that you were getting electric build-up in the quartz between night and day maybe, or winter and summer, or freeze and thaw, and you could end up with causing electric discharges that would maybe build up in the environment or so forth when the environment is optimal. Maybe it's dry, or maybe it's the right amount of daylight or whatever, and they get these very high prevalence of ball lightning. And some of them, they've observed the ball lightning traveling in what appears to be a corkscrew fashion. And sometimes it's a ball and it travels across the sky and then hits a tree, and then it breaks up into a corkscrew. And then it hits another tree and it breaks up into a corkscrew. And so what I shared on the trailer image for this presentation was a natural ball lightning shot provided to me by Dmitry Baranov. And this is falling down, and you can see, if you look at that opening slide, there is a wiggling side to side, which may or may not be a corkscrew. And there is also this kinks in it. Now, I can tell you that in the VEGA experiments, we have observed exactly that. I have this reservation that until we get a good global shutter image on there, some of these could be put into question. However, what I think I will show you tonight, and I can tell you it is a complete honour for me to be able to show this to you. Really, it's a complete honour. I'm sharing this to you very, very raw, because I haven't been able to sleep for a couple of nights, mostly because to be honest, I worry that some fate will befall me and I don't get this published. And so every day or minute that goes by that this is not public, I get worried that, you know, the information will be lost. So it's not only a pleasure, but it's a relief to get this off my chest. Okay, so I'll just start with a video that Ken Shoulders used in his documents to talk about how ball lightning was always preceded by lightning is always preceded by a ball lightning. So I'm going to play this. I gave the link in the description here. So I'll play this here. So look at the ball lightning you're seeing there on the right. And you can see, now look at the one at the top here. Now, I don't know if I'm just going to check if you can see my mouse. Yes, you can see my mouse. So this is waving. This is waving. Now, I always thought the waving was just because it's finding the easiest path, and maybe that is what it is doing. Maybe it is what it is doing, but there does seem to be some fairly regular periodicity with this, and given the fact that this is moving around in a 3D volume, I could not now, in good conscience, say that this was just innocent trying to find the path of least resistance. Anyway, I'll continue to play this forward. So you can see the ball lightning moving forward here, and Ken argues that all lightning starts with a ball lightning that goes from ground to sky, sky to ground, or sky to sky to create the discharge channel. Now, since this video, I have been sent, and I think on our Facebook I published even more superior imagery of slowed down lightning strikes. But I think it's important to show this particular one because this is the one that Ken Shoulders used to describe the fact that ball lightning has that. And so if you look at the ball lightning fall down image from Baranov that's on the title slide of this video when it's over, and maybe I'll find it again. In fact, I can probably show you by going here. Can I go there? I can go up here maybe. I can go here, and I can show you on here. So what I'm referring to here is I just slip this in on the right here. This image here, you can see it comes down, but when it's coming down, it's not just coming straight down. There is almost a wiggle that we see in our VEGA reactors, particularly. You know, I will talk about a little bit of history on that before we move forward. But you can see the wiggle, and then there's a kink, and there's a wiggle, and then there's a kink. Now you're going to see absolutely astounding interactions between these structures. So amazing. But I think by the end of this video, I hope, if I can do it justice, you will see and recognize how all strange radiation tracks outside of the ones that look like rolling clusters have been formed. I know that's a tall thing to say, but I think I'm going to be showing you a very small segment of the voluminous data that we have, and that is not because I'm holding anything back, it's because I simply haven't got time and to process it all, and it takes a bit of time to process it and get it so I can show it to you. But I think in the bits that I will show you, there will be enough to deal with the observed phenomena. Now, the thing about this is that these ball lightning has been shown to be able to go into a dark mode where it is neutral, and many authors have observed this. I personally observed this with studying echo fuel. As I said, it went out of the fuel into through the container and through many layers of polytetrafluoroethylene, through a polycarbonate window, and then through the IR filter, and then into the sensor. So this is something that it can go through many layers, and Leonid Roitskev observed this when he was exploding metal foils, and he is often credited with giving the name strange radiation to this phenomenon. And what he did was he had like a water chamber, and he put a high current short duration discharge through a piece of, for instance, titanium in water. And he observed outside of the reactor, which was made of polymer and metal, and obviously there's water in the chamber, these structures coming out. Now, I will note that water does seem to be important, and I will come back to this in a separate presentation. And I've said that for a couple of times, but there's too much to do in this presentation. So he obviously had water. In our work with Amasa, he had water. In the work of Dave and Henk on the VEGA experiments, both of them don't have very good vacuum pumps. And in fact, it is my understanding, and maybe Dave can confirm in the chat, I don't think his is as good as even Henk's. And Henk was going for producing more excess heat and working at lower pressure and longer runs. Dave was going for more dynamic shots. So he was deliberately adding things, and I'll talk about that in a minute. So first, these chambers are essentially any basic chamber that you can find in a scrap heap. And for want of dealing with strange radiation, it was useful to have something that was ferromagnetic. That wasn't the case potentially initially, but it's something to consider now. And these are things that you can pick up for the scrap metal weight. And what happened is that Henk, he couldn't get, he didn't have a very large port on the top. So he had to undo these bolts and so forth. So he actually had to build his cathode up by putting in pieces of metal and layering them. And that's how we ended up by getting this. This particular structure here is because these had layers of brass on it. And the interesting thing is that that's a bit of serendipity, because what that led to was both gaps between the sheets vertically towards the anode and gaps between the sheets horizontally, and these left areas for potential parameter sweeping, because they were imperfect in their construction, imperfect in their placement, and so forth. Now, where Dave has added some extra advancements in terms of producing these traces, but the credit really has to go to Henk. The first one I observed was in Henk's one of Henk's video, and I shared that a number of weeks, maybe a month ago or more. And the interesting thing was, within about a week, Dave had replicated the phenomena, and he is deliberately adding a little bit of water and a little bit of ammonia, and this leads to shorter runs because you end up with the pressure changing, and then you don't get the kind of discharge regime that you want. However, what it has led to, in combining with the video cameras, it's led to a situation where these phenomena that you're going to see are quite easy to reproduce, in terms of they've been produced a number of times, and they are replications of what Henk did. But when you see this, and so if you look at the previous video that I shared on the weekend, and we'll go over that, there is some phenomenal interactions. It really does take you to step through, and that's why I wanted to share the raw file. So you can download the raw file. That was been there since, I think, Sunday night, or certainly by Monday, and you can step through and see exactly what I'm talking about. Now, what I've done, hopefully, on this stream is I've changed it from 2,500 kilobits per second to 9,000 kilobits per second. So hopefully you will be able to see more detail on the shots that I'm showing in a minute. But first I want to go through a couple of people's work who have reviewed some of the people's work in this field, because this will allow us to have some context as to what we are trying to demonstrate we are actually observing the mechanism for. So first off, I got here is some work of Zhigalov, who was studying Parkhomov's reactors, and the 225-day reactor and the woodpecker reactor. So I'm going to go to that now. So here's this, and I've shared the presentation, and I've shared links to the translation in the MFMP's YouTube. So here is the a sort of a nickel hydrogen reactor by Alexander Parkhomov. And down here is the woodpecker experiment. And basically this rod jumps up and down and creates sparks in the water. So note there is water in that second experiment. He used DVDs, and these have been talked at length by various authors. Now, the question about this, I think it's called tribology or whatever, or certainly the three-body effect, let's call it that, that's what it's certainly called, is where you have a thing rolling along the surface, is that you could imagine something, if it came down to a point and then changed direction, you might end up with something like this. And I'm going to argue something else is creating this. So I don't know if you can see this, but basically there's a point down here. Maybe I can zoom in. Let's see if I can zoom into that and give you a better shot of it. So it has this point down here, and then you have these two traces, which are these kind of what I call M&Ms. And then there's a divergence here, and he's got a blown up section here. And in fact, he puts it on a scanning electron microscope, and you see the actual damage to the material, the CD surface, the polycarbonate, I imagine it is here. And the interesting thing is that the structure on either side here is very, very similar indeed, coming away from this. And it's almost like they are in phase with each other and the same wavelength. This would imply to me, and the thinking is that something came in from the sort of top, sort of middle here, came down to this point and changed direction and came up here. Now, I will show you today extreme changes in direction. I will also show you today where something has hit a surface which just looks like a straight beam. When it hits the surface, it splits into two waves that are equal wavelength. And I believe that that is what you're seeing here. And when we look at Daviau's work at Fondation de Bruyere, I might have got that wrong. You'll see in a minute. He sees several multiple tracks, and I think by the end of this you will understand how those are formed, in my opinion, at least my opinion of how they're formed, let's put it like that. So this is Zhigalov's work, and he did statistics about, when they appear and stuff. Now, there's work by Lutz Jätner, who's a very affable German chap, and he's actually got several things in here from many, many authors. It's a very long document, and it's well worth the read, and it's on condensed-plasmoids.com, and it's called condensed-plasmoids_lena.pdf. And that came from, and here it is, and that actually came, condensed plasmoids, from Winston Bostick, and this is a parallel thread to the start point for John Hutchison. So essentially, Winston Bostick was looking to convert the H-bomb into fusion for humanity, like fusion heat energy or electrical energy. And he was starting with discharges, and he was flying these things over magnets, and he was seeing all of the things that you would see in the celestial bodies being formed in terms of the sort of overall macro structure. When Ken Shoulders wanted to try and explain the lift and disruption technology and apparent transmutation and so forth technology of John Hutchison, he went to the work of Winston Bostick. So Winston Bostick did observe some things which are critical, and John Hutchison really provided the impetus to take this to another level. And so these are lines, and we're going to look at this in Daviau's paper, but he saw tracks, and on one side you see the spiraling going in one direction, and then on the other side you see the spiraling going in the other direction. And for me, this makes sense when you have pairs of what he calls monopoles. He says it's a Loschak's monopole, but you can debate the kind of monopole. And then you've got these tracks where you have these two lines, and you can imagine a torus going through a surface and leaving these. These are the more trivial type of lines. Now, these are the lines that I think are more interesting, and I'm going to immediately deal with this because I've got the video loaded into the browser. These are lines that either diverge, so you have one line and it goes into multiple tracks, and then this one where it has multiple parallel lines, or this one where it has a big beam that splits into many filaments, and then it comes back to being one beam. So I'm just going to go back to the last presentation we had, and it is this one. And so the first track here, is this kind of spiral track here, I argued was equivalent to this one, and I believe that this was done possibly in the in the 1980s. This image was taken, possibly no later than the 90s, which means that this is other than Solin and Matsumoto, they're probably contemporary. This may be prior to that, but it is this classic kind of strange radiation track. And if you imagine that this is either a linear, partially unwound ring of these highly magnetic ball lightning, or it's just one and it happens to be moving in a particular way, and I will argue later that it is following its own magnetic beam. It has its own magnetic influence, but ahead of it, it fires a magnetic beam in the direction it's going. And that can be a magnetic beam that's south or north, even though it's traveling, because like I can get a magnet. I've got probably some around here somewhere. This is probably not the best magnet I could use, but I've got these little cube magnets here. And I could have the north, let's say it's here, coming towards you, or I could turn it around, I could have the south coming towards you. So kind of imagine it like that. And the south and the north have different rotation on them when they're coming from a source like that. So I believe this could be one of the first strange radiation tracks, and it wasn't even noticed by the author, it would seem. The second one, which I did not show in the previous video, in fact I found it afterwards, and this is the nature of the data, there's so much of it, is this track here. And it's really quite spectacular. And at first, I must apologise, because someone said, do you think you can get 3 in a track? And I said, no, and I think I'm wrong. And I think that this is actually 3 in there. And I will show you the formation of a similar track to this within this presentation. Now, they can come together and they can go apart. In this case, they seem to be well bound together. So I believe that there are at least 3 in this. And so you can see a repeat. So you've got this one, which is here. That's the repeat on that one. Then you have this one, which is the kink on this side, and that's the repeat on that one. And then you have the one in the middle, which is kind of like a lower amplitude. So this is like braided hair, you can imagine it, but except they're all going around in the same direction rather than one over the top of the other. And so this is, for me, a rather spectacular little track, and this is a rather low quality GIF. But again, you can download the full resolution image here. Now, this reminded me of a track that was observed on Dmitry Baranov's experiments. And this was done, I think, in 2012. And what you are seeing here is a typical type of ring structure that you might see produced by Daviau or Matsumoto. And we saw this on the 10 yen coin exposed to a master gas, and in other places too. And in fact, I have that in full 3D with elemental stuff, which I will show at some point as soon as I can get to do that. But you can see overlaid onto it, it has one of these kind of braided structures. You can see here this braided structure. And he's done a confocal microscope lens analysis of that, and you can see that the way it's manipulated this, it's silicon with a gold film on top. And so it's manipulated it, and it's actually gouged out a layer in that. And I believe that it's very, very similar in morphology to the one that you're seeing here. Now, what I'm saying is that whilst you can produce these, Ken Shoulders and many authors, including myself, have observed phenomena that can only be explained by these going into a neutral state and then becoming re-excited in order to be able to damage the witness material, or in my case, the webcam that sensor that it impinged upon. So you have something created in a reactor. It can get into a state where it travels through the reactor, and it then comes out and leaves these traces. And it's still got this coherent matter layer. And when that gets excited, it goes into white state, and it can act like that ball lightning did, the technological ball lightning did in the VEGA experiment, where it literally chopped the wire, the tungsten wire. And so it does it, in my view, absolutely effortlessly. It's taking no effort, and so it almost does not see, as I said in the last presentation, it does not see the material that it's manipulating in this way. And so this is actually, here is the video that you can go and download, and you can run through it with me frame by frame. But this is the video we're going to be looking at in a little while. Because there are several interactions. I'm going to focus a little bit more on this, but it's this overall zone over here that I'm going to run through. And again, you could do this in your own time. But if you thought this kind of structure was a one-off, well, shortly after, I was looking at a video, and I am going to show you that video now, and it's here. And maybe I can pull this up here and put it there, and maybe I can make that bigger. Right. So in this video, it's a two-camera shot. There's one camera over here where there's not a lot of action, and then this is the side where there is quite a lot of action. And down the bottom here, you can see the frame number. Hopefully, it's at the moment 1101. And what I've done is I've put that there so that you can see on the replay of this video when I'm going forwards and backwards. Right. To start with, I'm going to pull it all the way back to before this session, because I want to show you something that happens when we are doing these recordings, and it sometimes happens, it sometimes doesn't happen. Firstly, you've got something that looks like a solar prominence going on down here. You've got two beams coming out and going down there. Hopefully you can see that. Maybe I can actually zoom into that. But zoom forward. Now, this is a problem that we do have. You should be able to see this. There is glitching going on here. Now, this might be because it's it's highly compressed, in that it has maybe keyframes every so often, and then it's trying to use the previous frame to make the subsequent frames. And this might be a situation where the change is so great that it can't encode the difference and gets confused. Or it may actually be some sort of glitch caused by what's going on in the reactor. This is why it's important for us to be able to record without compression, 444, ideally, or at least 422, so that we can get rid of this artifact. Now, we're going to come into the moment of interest here, and you'll see it very shortly. I'm stepping through. Okay, so this is the first one I want to show you. It's over here. Now, I'm probably going to have to zoom in a little bit more, but I'm going to step backwards and forwards on this so you can see what I'm talking about here. Right, I'm going to have to zoom in because you probably won't see this because of the stream encoding, but like I say, you will be able to download this video. So what you're looking at here on frame 1106 is something that's come out of the cathode area, and it's shot across, and it's to this point here. I'm going to step forward to the next frame. What it's done is it's actually hit the cathode here, and as it comes up, it splits into at least two fibers. Now, I'm only showing you this example because it's a simple one, but there are other examples where there are much broader range of splitting going on. But anyway, this is an example of where you have something that's one track, it then splits into multiple tracks, and then it cut up here, it merges into another track. And this is what Ken Shoulders said he observed many times when he was forcing EVOs to go through a small track. What would happen, a small gap rather, you would have the EVOs fan out into a lot of smaller EVOs, and then when they came out the other side, they would join back together. So for some reason, they are kind of locked together, even though they are, they're going through and they actually appear to split up. They are still one, but they are able to be in multiple places at the same time and then come back into a beam. And this is a not brilliant example of this phenomena, but this is the first thing to show you on this slide. And really that was not the best example to describe the phenomenon that is pointed out here. We're going to look at this where you have branching, but it's this where it comes along, splits into multiple fibers, and then goes back into one, and it's split into multiple fibers again down here. So that's that one. Then this is again the replication of where is it? This track here. So, but in this case, it doesn't appear to have the secondary element to it. It seems to just be the first element. So it's kind of like bouncing on its own magnetic beam. Let's put it like that. And you can see just the tail end up here. Now, there is a video, an image in this presentation by Lutz Jaitner. Now look at this. This is a track recorded, and I don't know the author. This may be Daviau, Claude Daviau. Oh no, and this might be Rodionov and Savatimova. Irina Savatimova was a real pioneer in this. Now look at this particular track here. You've got bounce, curve, bounce, curve, bounce, curve. This is not too dissimilar from this particular track. It even has this kind of semi-webbing-like section under here. See this? I'm going to zoom in so that, yeah, you don't have to take my word for it. Here we go. So it's got this fuzzy area under here, this fuzzy area. Maybe I can actually go to 400% there. And where does it recenter it every time? That's not very helpful, is it? Okay. And here's when you can see why we need to have a higher fidelity. Okay. But it's sort of got the webbing here, sort of got the webbing here, sort of got the webbing here. But here's what it does on a witness material. So it's really quite beautiful when you see it like that. Okay, so I'm then going to show you a range of other tracks here, and then we'll get on with it. So these are some open-ended loop tracks. These are some splatter marks. We're not going to be dealing with those today. This is one which I think is important to show now. This is a very famous one. It was taken in 1983 by Ken Shoulders, and this is not the best version of this. But I like the fact that it's done at 19 minutes past midnight. This is a man after my own heart. And it's a breakup of one of these structures, and it's definitely two in this case that are twisted together. Here's the one that we've just looked at. These are by Savatimova, I believe, and you see helical tracks here, and this might be two braided together. This is definitely more like a braided one. You can see very, very similar to the structure that we've observed. It's two or three. This might be similar to the one that we've observed over here. And when you've been through this video, you will see, I think, many examples correlating. So it's probably something like this one here. If I go there and I got the right, this one here maybe, this twisting. Now, if you look at the twisting and it's very fine, it will end up producing an M&M. So what are we actually seeing? I don't know, but I think we're getting very close to understanding what we're seeing. Okay, so let me go back to condensed plasmoids. Now I'm going to load up a presentation by Daviau because it has several points. Now here's a whole range of different tracks. So you've got the M&Ms and so forth. And he believes, this is Lutz Jaitner, that they are twisted. It's like a long ring, and then they're twisted and twisted on themselves, and then these can produce these tracks. I think maybe you can make your own judgment as to whether that's the case, having seen this video. Okay, so I'm going to go to this paper, So give me my shot. If you've got any questions that for me, ask right now, and I'll try and discuss them before as I get this thing up for you. So I am looking for. Okay, no questions at the moment. So I gave the link to this for people to look at if they could before the start of the presentation. And I like this because it's something that people could relatively easily do. Okay. Okay. So this is from the Fondation Louis de Broglie, and it's from 2013, and it's by Claude Daviau. I'm sometimes not so good on French names, so I apologize. And it says, abstract, we review and discuss in some detail tracks recorded on X-ray films following electric breakdowns in water, as initiated by Leonid Oretskiev, and we suggest that they are the result of the production of light magnetic monopoles theoretically predicted by Georges Louchak. So, almost 15 years ago, Leonid Oretskiev et al. Published their findings about radiation emitted by high voltage pulse discharges in water of the kind used in electroforming. The various properties of the emitted radiation shown in these different experiments point towards the assumption that the associated particles carry a magnetic charge. These monopoles or associated secondary particles, and that's important, hold that in mind, associated secondary particles, leave characteristic tracks on several materials such as X-ray or nuclear emulsions, metals or silicium, I think that's quartz. These tracks look very different from what is usually recorded in particle experiments and justify closer analysis. Okay, so did someone ask any questions? I don't see. There's a lot of talking. I don't know if there's any questions. Okay, I'll carry on. So this is kind of experimentation there. You can go and look at this in your own time. The films are exposed in two different ways. Firstly, they can be placed in the vicinity around about 50 centimeters of the container. In Oretskiev, he had things even 70 centimeters away, and thus exposed during a very short time, showing relatively few tracks. A second method, initiated by Leonid Oretskiev et al., consists of putting the content, water, powder, resulting from the fusion of the wire, of the inside of the container in a small glass cup, 6 centimeters diameter, and placing the X-ray film on top of it, a few millimeters above the water surface, and waiting a score of hours. More tracks are recorded in that case. In some experiments, an electric field, an idea of Georges Louchak, perpendicular to the surface of the film is applied to the whole device by means of two copper plates. Applied voltage is 10 volts. The film is then developed in the standard developer, fixed and observed with help of different devices. The tracks obtained by both methods, instantaneous or delayed, share the same characteristics. In the following, we shall comment mainly on tracks observed by the second method. And the important thing is here, 1, you can observe tracks from the experiment whilst it's running. 2, you observe more tracks by taking the water that had the exploded material in there and putting the film close to it and have 6 centimeters a diameter container and putting close to it and then having a field across that. So here's the basic tracks. Now, essentially what he's saying is that most of the tracks are just spots on the film. They're like impacts in the film, like it's coming out and hitting. But sometimes, much more rarely, you see tracks going across the film. So the majority of the tracks are going through. You see some like this, and some like this, and this is kind of like an open-ended one, but here's the type of tracks that he's observing. Now this is the same kind of spiral zigzag track that I believe that was observed by Solin in 1990, prior to 1992, and by Shoulders, without realizing it, probably in the 1980s. These are the tracks that you saw again coming and splitting apart into 3 separate tracks. And this, I think, is very, very telling. And I've got this in Photoshop at a much higher resolution. So I'm going to pull this out because you can see extra detail. And this is all in the PDF in the link. If you download the PDF, now you can see that the conglomeration of what appears to be at least 3 tracks is similar, in my view, to the one that you see in our VEGA experiment that has done by Dave that I've put together here. I believe it's something similar to this kind of structure is going on in here. And then what happens is, over here, one of the 3, or however many it is, comes off and goes off on its merry way, and a number of them are still maintained within the core of the plasmoid. And what's also interesting here is that you have this, in this latter section here, you have this central channel which looks like it's more disrupted, and it actually, if you look at it, it even looks quite like a coil. If you look at that, I don't know if you can see that. It looks like almost like a twisting, tumbling coil. But on the outside, you have this boundary, almost like it's cut a cylinder through the witness material. Also, the ones that you see that are burrowing straight through, perpendicular to the film plane, are these kind of ring spot structures. And often they have a pentagonal or hexagonal structure to them. So these are all important features in my mind about these type of impact marks. But this experiment is relatively easy to replicate. So then there's this one where it appears you have a track coming together, and I've again got this at a higher resolution, so we'll have a look at this here. And so it would appear that you've got either some 2 coming together here and coming apart, or this one's coming in and joining this. It's not so clear. If I do a contrast adjust, you can see it. There's a bit of rippling going on here, and then these are both kind of smooth when they come out the other side. And then that, he doesn't just stop there. He has this lovely track here, which is, again, if I pull in the Photoshop image here, you can see that this has a lot of substructure going on within it, and it has the secondary track that runs alongside it. Now, I'm going to try and show you how that could possibly form within this presentation, and it will absolutely be mind-blowing. When I saw it, it's like, it has to have such an intense field. What you're going to see is tracks that are interacting in 1/300th of a second. It's astounding what you're going to see. But I'm giving you the context here. So there's others here. Now, the interesting thing is he looks at these with confocal microscopes. He looks at this with another SEM and so forth. You can see here, this is maybe a similar track to what we're talking about here, but a slightly different structure that's eaten its channel through here. You can see these sort of curved outside here, but these bits poking through, and they are regular. And so you have a big one, a big one, a big one, and a slightly smaller one, slightly smaller one, slightly smaller one. So you can imagine it's something similar to this structure, but it obviously left the inside of the reactor, had to be neutral, and then it interacted with this witness material some distance away. And in this case, they were using water. So they talk about this. Now, there's one other thing that there's a lot they talk about with magnetic monopoles in here, but I think this is quite interesting before we move into the actual video analysis here. It says, the dish containing the remains of the titanium wire. A completely different behavior has been observed twice as the magnet was approaching one of these particles. This is the dish where they put the reaction products from the exploded titanium wire in water, and it has this sort of layer on top. So I will read from the page above. It says, a second observation has been made twice in the experiments performed in Nantes. These rather exceptional 2 out of 100 events are very suggestive. As we have said, the remains of the wire, a metallic powder, is dispersed in water. It's placed in a shallow glass dish 10 centimeters in diameter. Part of the metallic powder is composed of spongy particles which float on the surface. As they contain some iron, they follow a magnet, being moved near the surface with a velocity not exceeding a few millimeters per second. A completely different behavior has been observed twice. As the magnet was approaching, one of these particles, the size of about 0.1 of a millimeter, crossed the dish so quickly that the magnet did not have time to be moved during that fraction of a second. It is estimated the velocity was about 10 centimeters per second, i.e. 100 times the usual velocity. The only explanation in accordance with the laws of electromagnetism and fluid mechanics seems to be that the presence of a magnetic charge on the particle. Magnetic dipoles cannot behave this way. Now, when you look at this structure, these tracks in the video I'm going to show you, please bear in mind what they are saying there. From a very long distance away, with the same strength magnet, it was moving these particles around very slowly. Something leapt across through the water very, very quickly. Extremely highly influenced. So he's arguing that the only thing that could allow that to happen is that there is a magnetic charge on there. And presumably, if he was presenting the south pole of the normal magnet to it, it would have been a north magnetic charge. If he was representing the north, it would have been a south magnetic charge. And so what we seem to have observed are that these structures can get to a level of organization where they present a pseudo-magnetic monopole, where one pole is highly suppressed. I'm going to pause there and I'm going to see the question. So I see there's some capitals here. I assume you're asking questions with capitals. So, how... Okay, I'm going to look at the first thing with the capitals. Does this explain gravitational lensing? What of the cold neutrinos? Possibly. It would appear that neutrinos at least have a very small magnetic moment. I'll discuss that in another presentation. But if you had extremely high magnetic structures, then maybe they could lens it. What is gravity? So certainly, I think it was in the 1950s, a Japanese researcher suggested, before they were really discussing cold neutrinos, because neutrinos had only been discovered, I think, 2 years before, or shown 2 years before, that all gravity could be explained by neutrinos as the carrying medium. And in fact, in the I think 2010, a group from CERN, and I had this, I think, in my introductory video to Space Earth Human. You can go and look. I think there's a QR code on there. You can go and have a look at it. Or certainly in one of my trailer videos up to that. They were discussing at CERN that all the cold neutrinos could explain the way gravity works, and they have a large paper on that. So gravitational lensing of cold neutrinos, I think, we're closer to what's going on, and I'll be dealing with that in another presentation. Okay, so Are phase transitions just molecules changing their frequency? Gardy-Pierre, phase transitions. If I have steam and it condenses to water on my skin, I feel a burning. It's going from the gas phase, assuming it's dry steam and not some other steams, which people like to claim are steams, dry steam, but dry steams, and it's going and condensing to water. My hand gets burnt by that extra thermal energy that it releases. If the water goes to ice, then heat has to be released. What I'm arguing is that you are creating something much, much, much more dense, and therefore all of the energy has to be released for it to condense further into a different phase. And in the case of Lutz-Jaitner, he calculated for the ring, the torus-shaped, what he calls condensed plasmoids. He said that the density is that of a pulsar, which is a neutron star, something like 5 times the density of the center of our sun. And you can imagine that that had to release a lot of energy to get into that state. Okay, so if you're taking like from plasma to gas, then gas to water, and water to solid, and then solid to this phase of matter. And this phase of matter, if it compresses a little bit further, you get a boson over a neutron star, effectively. And also Lutz-Jaitner calculates that in those ring structures, those ring EVOs that he calls condensed plasmoids, there is a magnetic field that's about 50 million Teslas. 50 million Teslas. Now bear that in mind when you see what I'm going to show you in these videos that I'm going to show you in a little while. Okay, where did the EVO get all that power from? As usual, the energy density is almost unbelievably large. You have chemical energy, then you have nuclear energy, and this is a level of orders of magnitude larger than that. Go and see what Boyd Bushman says in that interview that I shared on our channel, but it's and I did a transcript of on CMET, I think. And he's talking about that they have been researching for some time at Lockheed Martin the next level of energy. And in the same conversation, he's talking about the being a neutrino universe. That aside, there's another level of energy to this. And what is that? Well, you imagine nuclear is 1 million times more than chemical. This is several orders of magnitude higher than that, because you are converting, for instance, the mass of a proton into energy like light and leptons, charged and uncharged. And so you are able to decay matter. But in crushing the matter and releasing electrons and light, for instance, you are gaining energy that way by nuclear reorganization. So there's a number of levels of energy that can be yielded from this. And if you have a structure that's extremely good at being impenetrable, when the energy comes out, it's like this, the coherent matter is able to absorb it like a force shield. And in fact, Ken Shoulders says that the only thing you could defend yourself against a neutral EVO, or even a neutral EVO or an EVO that's been accelerated and it's become into white mode, it's just about to hit you, is a sheath of EVOs. And in fact, you know, it's no surprise why Ken Shoulders and John Hutchison in 1997 went to the producers and writers of Star Trek to explain to them what you need to put in your programs to let people be aware of what the technology is that's going to come down the line. But these are the things that you would make force shields from. And in fact, we witnessed something that looks like a force shield encasing a piece of quartz in a Lion reactor, where the material all around it is heavily destroyed, but the same material in a very specific shape, which appears to be something that's this self-organizing structures tend to form, this kind of like teardrop shape. It is affected in a very, very different and less extreme way. So these things can self-organize around something and prevent the more gross damage to it. I'm not saying that this happens at the eating of the trap happens at low energy. It almost happens at no energy. When the coherent matter comes into, when the EVO comes into the material, the electrons, if they are like in a metal, they're free, or if they are in an ionic material like alumina or quartz, they're no match, because it comes in, it gets excited, it gets all the excitement it needs to be able to grab those electrons, and it rips all of the electrons off, and then the ions which get left get swirled up into it and become part of it. And so this is the basis behind the propulsion technology that I was discussing in the previous video. But anyway, the sort of propulsion by mass rectification, it almost doesn't see it. And there's so much energy to be gained, and the coherent matter is so good at because when you give a bit of energy to a coherent matter, you're giving it to all of it at the same time. So you're not raising one part of it by a higher temperature over here and another bit by a different temperature over here. The whole thing's one thing. So the whole thing changes temperature. And so and it then emits that as according to Scholder's 2 kiloelectron volt photon, and probably throws off a lot of electrons if they're shedding them. And periodically, these structures, they seem to dump spheres or crystals of elements that may not be the element that they started ingesting. Okay. Evos could cut through Superman unless Superman could cover himself with Evos. Yeah, he would need Evo underwear. Well, if he just wanted to protect his investment, but for the rest of the body, he would also need Evo clothing, even Evo hair. He was, if he could protect himself, so he could have Evo beams coming out of his eyes, he could have Evo clothing to protect himself from being impacted, or if he falls off a top building and hits something, it basically doesn't affect him. And because Evos are effectively a conscious technology, just like my arm is, I'm asking my arm to move, so it's conscious technology. You can force the Evos to lift you. Anyway, I'm going to get back to the hard data here. Okay, right. So, let me load up a video here for you. And it's this video that I want to get you. We'll kill that one. Okay. Is this the one I want? I don't know if it's the one I want. Okay, let me see if this is the one I want. I don't know if this is the one I want. Okay, that's not the one I want. Okay. Talk amongst yourselves. Okay. I think I got it. Hopefully. Okay. Yeah. Okay. Yeah. Now tell me, can you hear the audio when I'm stepping through this? Just it's helpful if you can hear the audio. Okay. Maybe you can, maybe you can't. Can you hear the audio? No video. We should not be seeing, please. No video? Oh, yes. Ta-da! So, it's better if you have the video. Okay. Right. I'm starting to get afraid of EVOs. Question, what safety precautions do you recommend? I've done some videos on safety. I'm going to do a more extensive breakdown when I am preparing the supernova, which when I get my magnetic sheeting and something else, then I will look at that. So can you hear this when I'm stepping forward? I don't know whether you can. I know what I'm going to... Yeah, you should be able to hear it. Wait. Let me do this. Ha ha ha. Okay. Oh well. Let me do this. Audio. There we go. Right. Okay, I can hear it, you can hear it. There might be a little bit of echo here, so I might kill it my end because it's not so important. Okay, right. So you can download this video. It is available on the remoteview.icu, and I will take a slightly larger chunk of this, do what I did with the other videos, and I'll do a real time and then a slow time one of it. So I'm just going to play this bit and you tell me if you can see what I'm talking about. You ready? You ready? Right, did you get that? Everything you need to do is there. Did you see it? Blink and you would miss it. Now, in 2015, I was told by Piantelli, don't tell nature what it is, let nature show you. And in 2010, Ken Scholler said to John Hutchison, you know, it's so easy to miss things. If you don't look, you don't even know what you didn't find. And those two things have stuck in my mind. And so sometimes you just have to spend time and go through frame by frame. And that's what we're going to do today. But actually, the key frames that are going to tell us the story are really not that many. So, which is good for you. Let's put it like that. So it's really not that many that you're going to have to suffer through here. Okay. Okay, so we can start here, I think. Okay. Now I might have to zoom in here. Right. So the first thing is you have this little beam across here now. I'm not going to get distracted. I love you guys, but... Right, okay. So, watch this structure coming. I'm going to zoom in and... Okay. Can everybody see that? Now, if the iris was open a little bit more, you would have... thank you, Slobodan. If you were... it means a lot coming from you. This is extremely bright, but because the exposure and iris is in such a way, it is not overexposed, and this allows us to see into the plasma. Okay, so let me show you what I'm talking about here. Now, watch this here, and Slobodan, you must thank Henk for his initiative. And he's been a pleasure to work with, and so has Dave on this project. They've taken a lot of risks to do these experiments, and it's a real honour to be able to analyse them and share my thoughts with everyone. So I'm going to step through this. Now look what happens. It comes out of here and it basically takes a hard turn. It takes another hard turn. And watch what happens. There's one initiated down here. Okay? And it's sort of coming up. Can you see my mouse? Can you see my mouse? It's not very large. And go like that. It bends as it comes round here. But as it goes round the other side, it bends around the top of it. Now, this is not the most extreme one that you are going to see by any shape or form. But it's just the start of what we're going to go through here. Now, there's another one here that comes out, looks like it's going relatively straight. And for some reason, just does a stupid kink like that. And as it does that kink, something appears in the darkness, where it's actually gone underneath whatever it was, but it was further over to the right. So you can't see it, it's in the darkness. It isn't glowing at that stage. But it's causing this track to kink. And it's this one. It's this one that's coming up here, which is this track where we saw this very, very interesting structure here. And we've done this in detail. Now, I told you in the last video that well, firstly, if we go to this sphere here, this illuminated part of the cathode here, and we step back, I don't know whether you're going to see this. I have, like I say, I've uploaded done the data rate, so hopefully you will. There is a spiral coming in, not going out, but coming in. So it's come from somewhere else in the reactor, and it's coming in to join this material here, and it almost looks like it goes through it and then gets energized and it comes out and starts re-emerging over here. Okay? I'm going to zoom in if I can to this because it's quite spectacular. I'm going to write in. Okay? So here we go. This is our structure. It's coming out. The next frame, you can see this is clearly a twisted structure. Okay? You've got one that goes around like that and one that's here. This looks like it's two. It's two twisting together. This is similar to the ones observed by Ken Shoulders in 1983. It's so sad that more people haven't done this work. But we're doing it now. Here we go. It's bending round. Continuing to twist. And these are 1/60th of a frame. So I'm going back, forward, back, forward. And then it comes to this point, and it's kind of bunching up. And the reason it's bunching up is because it hit the cathode. And look what happens. Next frame. Boom! Comes out. Boom! Right? It doesn't stop there, though. I'm going to zoom out a little bit. So we come back. Comes out. Boom! And then all of these tracks start flying out. And it goes over here. Now, remember what I said earlier. I'm going to show you something where a track comes out and it spits. Okay? Now, something has come out of here. It's come out so fast, but it's come out. It hits the cathode, some part of the reactor container here at this point. And then it goes boom. Not a boom, but a boom. And you have a squiggle coming out and another squiggle. And I'll go to the next frame. It's two squiggles. Look at the end point here. That's the start point of that squiggle. Look at the end point here. That's the start point of that squiggle. Now, let's go back to the presentation by Zhigalov. What I'm saying is that if you look at Daviau is saying that most of the tracks that they observed was when they did delayed detection. So you would get much less with an active detection. In the case of Zhigalov, he was using active detection. So most of his tracks would be spots, and you can see some spots on here. But in this case, you see this and it coming out. And there is a pit here. I think what happened was something similar to this. A track came out of the Parkhomov woodpecker, it hit the material and it blew up, travelled along the surface as two structures. And because they because they are born from the same coherent matter, when they reorganize, they're already in phase and the same wavelength. And so you get these things which are basically following each other, and so you end up with something that looks like this. Okay? Yes, lightsaber. Yeah. You just coat a I discussed this before. You coat a telescopic aerial with evos, and then you have lightsaber. It's light. It cuts anything. Yeah. You're very close to understanding what King Arthur's blade is now. Consciously controlled technology. We're getting there. Right, okay. Hello, my wife. Oh, good night. Good night, India. Right. You can also see there is another emission down in this side here from the previous boom, and that does something and it kind of dies over on the cathode. Now, I'm going to start talking about the real money shots here, and this is going to build to a fantastic conclusion, and as I said at the beginning of this presentation, it's really, really spectacular. Any dusts in the reactor? Yes, in these reactors, sometimes David adds other stuff like some hydrocarbon, or adds extra water, or adds some, oh God, I've forgotten it now, ammonia. But when these things explode, you are going to get very fine particles in there as well. And in fact, both Henk and Dave have observed their viewing ports very quickly getting covered up with a grey dusty stuff on it. And since EVOs tend to produce a lot of carbon, and I'm going to talk a lot about that moving forward, it's likely that a lot of the carbon, it's a lot of carbon dust that's being synthesized. And that's why this is what you need to terraform. You go to a planet where it doesn't have material that you could use for life, and you make the material for life. Okay, so we're going to go step back in this, and I might have to just come out a little bit. Okay, so it's actually very few frames. I think the core frames are only about 3 or 4 frames. And bearing in mind, this is 60 frames a second. Right. Watch. I'm going to zoom in. Maybe I can get this to 200% and you see everything that's important. Okay, here we go. So I'm going to call this one here number 1. I'm going to call this one that bends round here number 2. And I'm going to call this number 3. I don't want to be number 2, but it has to be a number 2 when you've got 3 numbers. Right, so there we go. This one's just bending round. It doesn't seem to be doing much. It looks a bit kinetic at this point. This one's coming up, but it seems to bend round as it passes this one. This one does a 90-degree turn. Okay? Now, I'm going to go and hold my mouse at the end of this point here. As I step forward, this is the beginning of that track, right? Now I'm going to put the mouse at the end of number 3, and I'm going to step forward. This is number 3 continuing, okay? So I'm going to step back. This is number 1. I'm going to put my mouse at the end of number 1 and step forward. Number 1 comes up, and it feels the influence of the incoming number 2, and it bends around it. It avoids it, and then it bends around it 90 degrees. But the influence, I believe, of potentially the anode itself, because the number 1 is traveling towards the anode, potentially the influence of number 1, this is slightly bending up, and then it turns around. It does almost 180-degree hairpin and comes round this side. And as it's going in the other direction, number 2 deflects number 1 in the opposite direction. It deflects in the opposite direction. So this is traveling, these are traveling from this spot, this bloom here, to here in 1/60th of a second. from here all the way around here, around there, and up there in 1/60th of a second. So the deflection around this 90-degree turn is maybe 1/300th of a second. Okay? And it's not even close. But the very, very, very interesting thing is, number 2 is bending around number 3, and number 3 is deflected by number 2, but it bends around 180 degrees, and before number 2 ever gets close to number 3 again, it's causing it to deflect. It's causing it to deflect. So that means, in my view, that the exotic vacuum object here is sending a beam of magnetic energy in front of it as it moves forward in the direction of its travel, and that the field around it is one direction. Now you can imagine that it's one direction if it's the North Pole and the other direction if it's South Pole. Okay, whatever it is, what we see on this frame is it comes around here, it deflects it to go like one way, and it loops back round and it deflects it to go the other way. The next frame is this. You can see number 1 goes round and then it goes in. That's the end of number 1. It goes in, right? And I'm going to go up here so you can see what happens to number 2. I might have mixed these numbers up, but you can get the idea. This one here then goes past, and it then becomes a squiggle over here. So in these, I think it's 4 frames. And by the way, I uploaded this on either Sunday night or Monday, so you've had this to play with. Within these 3 or 4 frames, you see 2 particles interacting twice with each other. This one and this one. These tracks interact once. Then it comes around here and it's already interacting with the track it's just interacted with again. This is astounding levels of interaction. It shows that the kind of calculations of Lutzietner and the kind of observations of Daviau, Fondation de Broglie, are probably correct. And that Solin in 1992, when he says this is creating magnetic charges, I think he's correct. When in 1986, Ken Shoulders published his book EV, A Tale of Discovery, and concluded in his book that these are magnetic monopoles, they're oscillating monopoles. And I'm going to show you something in the next sequence, which for me, it's the coup de grace. So I need to find that for you, and let me do that. Have you got any questions? Do you want to see anything here? Does everyone understand what I was talking about there? Have you seen Michael Claridge's work on the currents turn just like that within the Birkeland current? Oh, you're going to see some things that are just spectacular in this next video, just breathtaking. Oh, the Birkeland currents will probably be the same as this, and I discussed that in a previous video. Yeah, it might be magnetic, or it might be another force. What's interesting is, if we look here, these particles, this one looks like it cares about the anode. It's straight up coming from the cathode and on its way to the anode. But these 2 particles don't care less about the anode. You know, wherever they came from, I don't know, but they don't care about the anode. They care about each other. They care about influencing each other. But even the one that cares about the anode cares about these ones completely. Okay, let me dig up the other video because I think with this video and the other videos that I've shown you, and you will be able to explain for yourself. You can't unsee this. Once you've seen this, you will know that this is how it's working. It's just, I don't need to see a calculation. I don't need to say wave my arms and say, trust me. You're going to see this and you're going to know that this is how it works. It's how it works. It's like an apple falling off a tree. It's how it works. Okay. Give me just a little while to find the right video. Like I say, one of the reasons I'm showing this to you in such a raw fashion is because I can't sleep until this is out of my head, and you know that this can happen. It's not fair on anyone if something was to happen to me, and there must be other people that know this. I cannot believe that other people do not know this. But they're an also-ran because they didn't show it. It takes guts. It takes people like Henk and Dave to put the pedal to the metal and actually deliver, and they did. Real pleasure to work with you guys. Thank you. Thank you. Okay, here we go. And I need to drop it into a timeline to make it easier for me to show you. Congratulations, Henk and Dave. Really, seriously. What you're going to see, this is it's just beautiful. It's just beautiful. It's just beautiful. If I was a crying man, I'd be crying now. New sequence. And give me the video. Yes, I want to change the sequence settings. Where have you put me? Oh, not there. Can we see it? Okay. All right. Okay, I'm going to zoom out to give you the overview. I'll play the entire clip, and then I'll say, "Did you see it?" Okay. I'll move it over there so my ugly mug is not in the way. Right. Okay. I'm going to play this clip. Yeah, now I can finally get some sleep. Thanks, David. Damn you! I can't quite get some sleep because I want to record these things with global shutter so that, you know, but what you see in this video, it just is how it's working. It just is how it's working. Okay, so I'm going to play it through right now. So ready? Ready? Did you see it? 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 Okay, all right. That's been cool. Okay. Did anyone work out what I was talking about? Do you want me to play it again? Ready? Did you see it? Did you see it? Did you see it? Okay, all right. I'm going to step through this. Okay, so what we have is we have the cathode, which is our brass plate stack, which is the creation of Henk. And it's serendipitous, as I said at the beginning. It was created because he didn't have a very large port to put his electrodes into, and so he cut them up and put them in pieces and assembled them. But this gave us gaps between the things and gaps vertically between the plates. You saw it! Oh, so I can go home now. You don't need to see. Don't say you saw it. I'm tired. Okay, right. We already know the EVOs are spinning because we saw that in almost one of, I think, the third video of Henk's that I showed you very clearly. So I'm not trying to be a troll. Right, okay. So this is the cathode down here with the white glow. Isn't that where you've got this sort of violet purple glow? That is the anode. And so you can imagine there's a field going up there. And if you use your rolls, you've got some field spinning around this. So I'm going to step through this. And you've got several ejections. Now, the reason I haven't shown this bright one up here that you see where I've got my mouse, this actually comes from a previous explosion, but I've cut that out because that is one of these tracks, one of these frames that bleeds across several frames and is just a complete mess. But trust me, that came from a big explosion. It comes down here, and watch, it's just about to hit the electrode. Boom! It gets energized, I believe, with it takes a large amount of electrons off there, gets re-excited and comes up towards the camera, and you can see that this is a torus. Now, is it a torus or is it just out of focus? I don't know, but I will deal with these kind of structures in a separate video because these are dealing with the ring structures. What I want to do is these very complicated tracks that I opened the presentation with and gave you a lot of background spanning many decades by many independent authors, and I believe that what you're going to see right now is going to explain that. So, and I'm just stepping forward. These are the, okay. So this is the start of the money shot frames, and I'm going to try and go in a bit closer so that you can see what's going on here. So maybe I can get this all in here. So. Can everybody see that? Can everybody see that? Now, this again up here in the top left is the anode. The main sort of yellow-white area is the cathode. This is the ejection that I'm asking you to look at. This one over here, large, pretty much in the center of the frame. I'm even going to lose a bit of the anode for now, because this is the one that we're going to be interested in. Right. I'm going to step forward, and I'm going to change this to frames so you can see the frames down there. So I'm on frame 15 of this little clip. This is the clip that you will be able to look at. Right. So there's the end point, and now the new start point is here, and we're going down to here. And it looks like it's starting to bunch up. That's the end point. It looks like it's crashed onto the cathode. Now this was born on the cathode. Why is it coming out and going down? Is it just gravity? Is it just heavy? Who knows? But it's definitely not traveling towards the anode. So it comes down, it hits the cathode, and also it's going into the opposite direction of the spin on the overall plasma discharge. So it comes down, hits there, and what happens? It gets energized, and it goes in the opposite direction. So look, comes out, that's the end point of frame 1. That's the beginning of frame 1, that's the end of frame 1. This is where it gets stuck, and it kind of bounces and almost retro-reflectively comes back onto itself. It's now a squiggle. It's a squiggle, right? This is the end point of frame 18. We're going to go, oh, what's it done? It's bounced, it's actually hit the cathode on frame 17, it's come back on itself and it hits the cathode again and jumps a little bit on frame 19. So it's come back and it's bouncing itself on it. Now it's jumping off and now it's in the air and it gets caught by the spin field around the discharge. Watch, this is the end of frame 20. It's the beginning of frame 21. This is the end of frame 20. Now, this is going to get really, really special. It's coming out of here. What is this? This is another discharge coming out here. Look at this ejection here. Look at this ejection. I'm going to go back. It's coming along. This is the end of frame 20. Beginning of frame 20. End of frame 20. Sorry. Beginning of frame 21. End of frame 21. This is the end of frame 21 for this ejection. I'm going to put my mouse there. Now look what happens. This is the ejection from frame 21. I'm going to go back, ejecting out. This is the end of this new ejection on frame 21. It's coming in here and it's merging. It is merging with our big structure. The fine one over here is coming along here, and this is our big one here. Now watch what happens. We've got another ejection here, like dial on a clock. We've got another one here. At this point here, this is the end of frame 22. This is the end of frame 22 with the first structure. This is the end of frame 22 with the second structure that joined the first structure. Here is the third structure on the end of frame 22. Watch what happens. That is the beginning of frame 23 for the third structure. And it comes out, and almost the entire frame 23, it comes towards, and then it starts to bend into this conglomeration of the first and second structure that are starting to get into phase. They're slightly out of phase. One is a longer wavelength, or it's almost in phase, but it's slightly offset. Okay? So it's the same wavelength, it's just not in phase. But it's starting to follow the phase of the other one. Now this is coming out, and as soon as it gets within this range, note this range of this conglomeration structure, it loops round it. It loops round it, and this is probably 1/600th of a second. 1/600th of a second, and it's wrapping itself around this conglomeration of two, which is in the spin field, the discharge. Okay? Notice over here, you've got three structures coming out, almost equidistant, similar to these structures here. Hold that thought. Okay? Now, we've got the end of structure 2 here, the end of structure 1 here, and somewhere merging in, we've got the end of structure 3. I'm going to get the end point here on frame 23 of structure 2. They merged, spiraled together, and then they split up. It wasn't quite enough for them to join together completely. Wasn't quite enough. But for a moment in time, they were influencing each other to merge together. Okay? Now, look, it's difficult to tell which one's which at this point, but I'm going to go to the end of this point here. Look, it's starting to accelerate. That's that one. I'm going to go to the end point here. It's starting to accelerate. That is that one. I'm going to go back to there. And then this one here, it starts to accelerate. Right. Now you're going to see something that's absolutely mind-boggling. It's mind-boggling, right? Okay, so here's our three traces that were grouped themselves together and then now came apart, okay? And I believe that if you were in one of these structures, that you would create these kind of... So basically, this structure is two that were kind of like merged in on this one. And this one here, where is it? No, it's on this one. Sorry. This one is three that have come together, but all of the organisation happened within the plasma, and they cohered and were locked together and produced something that would produce a trace like this, that would produce the similar traces to the Daviau saw. Okay, so you got it here, coming round, and I need to move over a bit. Now this is the brightest one, and this is actually the original one. If you trace it back, and I've done it, and trace it back, it's actually the original one here, this brightest one that you got left. The original one we've been following since the beginning. Now watch this little trace here. If you can see that, I might have to zoom in to 400% at this point. Right. I'll come in even closer now. So, What I'm looking at here is this little trace that's come over here and bounced over here, okay? It's kind of done this. Look at it here, right? Oh, no. What have I done? Oh, no. What frame am I on? Okay, here. Oh, no. Sorry, I lost it a sec. Apologies. I don't even know where I am because I'm so zoomed in. Okay, apologies. I'm going to have to come back out so I know where I am. How annoying. Okay, boom, round, 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 round. Okay, this frame. Okay, go back in 400%. Sorry, this is the best way I know how at the moment to do this. Okay, so this one that's coming around here, and this is the remainder. It's the brightest bit in the field, and this is the remainder of the original trace. And watch what happens. That's the end point, and that's the beginning point. Look what happens to this. It comes down, gets within its event horizon, literally takes a 180-degree instantaneous direction shift as it gets caught in the spin field of this one, and it does 180-degree motion. 180-degree motion to this point here. Now watch what happens on the next frame. I'll move it over. Here it is. Here. Oh no! What happened? Have I got that frame? Oh damn it! I haven't got that frame. Ah. Right. Give me a second. I need to go find a different video. Oh dear. Oh no. What I can tell you is, and I will go and find it, but what happens is this one in the next frame immediately starts orbiting around this train. Once it's gone past it, from the end, it catches up with it and starts orbiting around it. It's spectacular. But yeah, what's happened here is this particular plasmoid, not all plasmoids are built the same. And before I go and find that there, let's go back. Not all plasmoids are built the same. And what I'm arguing is, and have argued for a very long time, is that it might look the same scale, but because it's a condensate, it can have trillions of times more matter in it than one that looks the same scale. You understand? And so it can have many orders of magnitude stronger magnetic field on one of them, whereas many of them are just not as good. Not all of these are built the same, but this one which we followed from the beginning all the way over here, and I will go and try and find the video in a sec. So let me just trace it. It's born here, comes over, comes down, hits, bounces back, hits again, bounces up, and then starts following the field going round. Then this one comes in, joins with it, starts getting in phase. It's in phase by the time the next one comes in and loops itself around. It's almost like this one its entry point is not correct, and it knocks it out of phase, and the whole thing starts to dissemble and dissembles. And the original one is the brightest, and it's left. And this one, the brightest one on the entire page still, on the entire image. From this point, it comes along here, and this one, when it gets into its field, it literally does a 180-degree rotation. And in the next frame, which I'll go and find for you, from this point onwards, it starts spiraling and orbiting around this structure. Not only, Gordon, are they got an intensely spinning field around it, they fire out a beam, an intense magnetic beam in front of them, which we demonstrated in the previous video. This is some of the most spectacular frames that I've seen in my life. I don't know what floats your boat, but this floats my boat. This is really, really impressive in terms of the actual science that it's showing you in visual. I'm not having to calculate this. I'm not having to look at the sun and put it into a supercomputer. I'm just looking at these video frames that Dave's taken with a what do you call it, a iPhone, and by stepping through in like 7 frames or 8 frames out of 60 in 1 second, you are seeing absolute goldmine of data. Absolute goldmine of data. So, with that in mind, I'm going to let you talk amongst yourself. Ask any questions right now, and I'm going to go and find the last frame that I want. The last frame, which I happen to appear to have cut off here, and I'll show that to you. So let me go and find that. 610. Okay. Ooh, I know what I can do. Haha. Yeah. I can use, well, maybe it'll work. Why didn't it do that way? Oh no, come on. No, it's not going to let me do it. Okay, alright. I can find it, don't worry. Okay, alright. The good news is, I found it! Yay! As I said before, if I had more time, I'd have done a better presentation. Okay, all right. Oh, I just love this. It's just love it. Oh, man, wow. It's absolutely madness. Right. Okay, so back, normal programming has resumed. So look at the end of this. This is our bright trace, which is starting to die as it comes out of the exciting area. Remember, as it touches the cathode, it gets a bucket load of electrons. It really gets excited. But as it comes around and even leaves the discharge area, it's got less electrons that it can consume. And so Ken Shoulder says, to keep it charged, it likes electrons. It eats electrons. It feeds electrons. You feed it electrons. And so if it hasn't got electrons, it starts to go more and more neutral. But it's still got an incredibly intense magnetic field, or some sort of field, that is causing this. This is the end of the original thing, and this is the end of the one that's done this 180 loop. Look. What happens? Comes round and it starts to orbit. Now, the implications of this are that you can have a trace going through a material. And what happens is it's so magnetic that it picks up bits of magnetic material. And as it does a cycle, it's smashing that piece of magnetic material into the witness material. Is this one type of artifact you get when you get parallel traces? It's something that keeps getting hit and it's bouncing along the surface and it keeps getting rammed in and rammed in and rammed in, and it cannot resist the intensity of the magnetic field. Okay, that's one. Or two, you have something like this, where it is captured another exotic vacuum object and then it becomes entrained with it. It's like it's a drone. It's like like you played those old 1980s games and you got like a little buddy that sat over here and shot out the bullets as well. It's kind of like that. The main one is going along, but it's picked up something else that can go along and do damage alongside it. And it may have a different spin. It may have a different spin. So this, for me, explains the kind of track that Daviau is talking about in his paper here, where you've got parallel tracks and other types of parallel tracks. This may be just normal. When you see this now and you see these wiggles, it doesn't seem so ridiculous. And these 90-degree turns here, what is a 90-degree turn? Well, remember what he said. Most of the tracks are going through the perpendicular through the witness material. And so we've already shown that if you have two tracks, one's going like this and one's going like this can cause it to go around it. So this isn't the track itself deflecting itself round a curve. It's probably another track that went nearby, which may be extremely small, but has this incredible influence over the other track, as you've seen in the video. But as it's doing its normal traveling along, it's got some wiggles going on. And in this video, which I will share, and like I say, what I'm having to do is I'm having to scale it to 4K, so that when you view it on YouTube, the YouTube algorithm hasn't compressed it and you lose all of these fine details. But also, the smaller segments I will publish so that you can review them in your own software. But you will see many tracks doing all kinds of things like this. But I think it was a nice journey to watch that one. I'll step back and you can see all kinds of different tracks here doing different things. So look, for instance, this one here coming up, and it literally gets to this point, and it goes round. It's even almost doing a 270 on itself. There's the glitch track that I was talking about, and you'll see many extreme interactions. So look, this track coming out here. And there's another one still launching here. And it comes around, it bends around this one, comes up here and bends over the top of this one and tries to go on its way. These things are not kinetically moving. They are interacting with each other. Look at this one. It comes here and it bends round this one. It literally bends round it. This one coming up from here, round here. And it seems to orbit around this one here. And there's our friendly ones that we saw earlier with our loop. Anyway, I think in the videos I've shown you today, when you understand, and hopefully it's pretty trivial to see what's going on, the kind of track that you are seeing in this shot here, which I believe is the type of track that produced this track, which left this kind of damage onto the silicon and gold wafer plate, is formed in kind of this way, with multiple things coming together and cohering into one track. And if you go back and look at the video here, you can actually see that this is a packet of waves that are traveling in a direction. And again, this is the anode up here. This is the cathode down here. It does not care about the anode. It's going in this direction and nothing is deflecting it. And then if you go back to Daviau's work, what else we got? He's got his magnet tracks here. These ones, easy to explain. These ones with the matched tracks alongside. So you've got this matched track alongside here and another parallel track here. This one here could literally be a piece of magnetic material that just gets pulled along with this intense magnetic field on here. Or it could just be another one that's less powerful that gets entrained. Again, this one here, but this one's a more interesting one. You see it's got a substructure. And we've dealt with the splitting tracks like this, which it's actually better if you look at it in Photoshop here. Splitting and joining tracks, dividing tracks. What else we got? Yeah. All right. Well, I think that's. I did a combined shot here, which is not very good because I didn't have a lot of time. But you can see here the overall combine. After it starts moving in a direction here. So you can see, where is it? You can see the segments here. This is one segment, this is another segment, this is another segment, and then this is one segment, and you can see the joining in and starting to phase lock. Then it's phase locked here, the next one comes in, but it's just a bit too much from it. It breaks up, and it gets a bit faded down here, and then we have this loop around. Anyway, I thank you very much for your time, guys. I'm going to take any questions, and then I'm going to go. Right. Do you have any questions? I got one. Gardy, you got a question. Okay. What's your question? Thank you, BP. But listen, this is... I had the pleasure of speaking to or seeing Irina Savatomova today. I have actually some other slides here actually, which I think probably this is from Ed Lewis, and Ed Lewis has done some fantastic work on condensed plasmoids, and I can show you it here, and it might even give you French subtitles at the same time. So let's see what happens here. Oh no. It's covering up the French subtitles. Okay. Maybe if I move my mugshot down. Can I do that? Do I want to break something? Maybe I can move it down. Let's move my... no, I can move that down. Let's move my mugshot down, then you can see... buongiorno. Oh, that's Italian. Okay. So these are a couple of slides from Ed Lewis. And Ed Lewis must be given credit because he called... these things microball lightning, and managed to convince Takaaki Matsumoto that this was microball lightning. And so this is one from Oroitskiev. There's a video that I just showed you with these things. This is from Baranov, and this presentation you can go and see on our YouTube channel. And what you've got here is you've got this ring structure, and that's one of those. These are a dual Evo impact strike here, and there's a single one. So, you know, you can see how this is lead glass, and you can see the crystal of the lead glass. As this goes in, it actually liquefies and turns to even more glassy glass than the glass around it. And he actually had these things go through, say, alumina, and then he put wax on the other side, and it didn't melt the wax. So this is absolutely non-thermal nuclear sort of disruption. These are from he he gives this like in, you know, it's a a rock being dragged across a mud flat. There's a couple of slides in here. So this is from Parkhomov's, one of Parkhomov's reactors from glass, and you can see these tracks within inside. And you can imagine, we saw these multiple parallel tracks on between the fuel and the plastic in 2017 in the Echo fuel. And these kind of tracks have been observed by many authors. And if you can imagine, what we've shown today is that when these things come out and they hit the change of impedance from the metal conglomerate of the fuel and the plastic, they split up and in many little tracks, and they go along the interface between the two. And because each one of them is like a little ball lightning, they score out multiple parallel tracks. So we observed that in Echo fuel container. This has been observed in Baranov's work, and he saw many of these parallel tracks. And from my mind, what's happened is it's gone in to the interface between the gold film and the silicon, and it's gone in between that interface, and it's spread out, and it's produced these multiple tracks. Here you can see the multiple tracks, and this is actually inside the glass, so somehow it got in there, but in order to burrow through the quartz, maybe it's quartz, it had to do this kind of disruption in this way. You see these parallel tracks here. Maybe you don't, because you're just looking at my face. I'm talking about this. These parallel tracks here, you can see, which is a close-up of this. And this is, by the way, in boron nitride. Okay, so this is not soft stuff. This is, Solin and Baranov. These are by Daviau. It's the close-up in Daviau. Now, this is interesting because this is by Daviau, and this is copper forming in these beautiful crystals via the transmutation of titanium. And this is delayed process. And so this was observed by Hutchison, and it's been observed by Savatamova, I believe. And so this is Dash, and Dash is observing over a period of time. So this is on January the 17th, 1995, and January the 19th, 1995, and February the 17th, 1995. And there is elemental shifts over a period of time as these structures are growing out of metal substrate. So that's that. This is the crystal of toruses that is in the Bogdanovich paper. It's a plasmoid cluster, and this is the actual torus itself. And so there we go. That's that. Okay, so did you see similar particles emanating in a Mars gas? We saw a strange radiation track coming from a cavitation spot out of the center of a cavitation spot and traveling out. And this was on day one of Project Omar. And the way it was observed by was using the dynamite and then using the polarizing filter. And you couldn't see it at all until you got the polarizer, and then it just popped out. And in fact, that's how many of these structures were observed. So yes, these tracks were observed on the what do you call it, the vibrator plates, many of them. And additionally, we observed on the 10 yen coin what looked like spheres of oxygen from copper oxide that is transmuted into sulfur, and it's called snowballs and cobblestones. And this was in a structure which looks like I think it's the Finnish university's 3D model of a supercomputer's production of what a magnetic monopole would be. It looks basically like that. And on one side it has these cobblestones, and on those cobblestones it has these little balls that moved around and transmuted material. But also on that same 10 yen coin, there's one of these very classic ring structures, and it has moved all of the diamagnetic copper has disappeared, and the paramagnetic copper has disappeared, and the diamagnetic zinc in the 10 yen coin remains. And so that is something to think about. do EVOs share electrons? I think what you're seeing here in this particular video here is an attempt to share and come to some sort of coherence between these structures. Okay? But it is unachieved before they fall apart again. Okay? I love the way that spins around there. It comes into the event horizon of this intense field. It does a 180-degree turn, goes round, literally comes back on itself, turns round, does a 180-degree orbit around, almost instantaneously, bearing in mind. This is almost instantaneous. And then from this point on, this has probably already gone through. It then starts to orbit around it. Where can I source MHHO? I don't know, but I think Slobodan Stankovic is probably the right guy to talk to. And by the way, Slobodan, I will be needing you later in the year. Is the white hole EVO producing a particle antimatter pair and black EVO deflecting the antiparticle? Well, that's a big question, but what I can say is Parkhomov is saying that when you have dense matter, and you can't get much more dense than the core of a neutron star, then you have hot dense matter, you synthesize neutrino pairs. That is a neutrino and an antineutrino. Now, obviously, there's some debate as to whether they're the same thing, but anyway. Yes, some of the traces do appear to be birds. Really, those things have been well studied, and they look like they point to the structure of the magnetic sort of magnetic pseudo-monopole structure. However, in this video, I just wanted to clear up a mechanism, well, not a mechanism, but at least a visual ABC for how these things can come together, form these structures that then explain all of the observed kinds of strange radiation tracks that have hitherto been very difficult to understand. You have something that's straight and then it goes squiggle. So here you've got something that's straight and then it goes squiggle. Okay, this is what you see. Okay, and then here you've got something that's coming down and it's going round. So in that Daviau work, you have something that curves slightly, then it goes into a squiggle, and then it comes along, and then it does a 90-degree turn. But I believe that's because there are other emissions that are coming perpendicular, and they are causing this kind of effect. And so it's not the track in isolation that's creating these wandering tracks. Shockwave, you might be right. Our hearts are biological plasmoids. Yes, well, they certainly got an energy, and so is the spirit and the mind. Hank, I'm glad this explains a lot. Like I say, hopefully at the end of this presentation, two things that I want to get out really in this presentation is that if you remember the video that I shared of not just the Hessdalen lights, but also the ball lightning from Australia, from the Australian outback, when you look at that video, it produced these spiraling motion in it. And so we have corroboration there on very big scales. The type of scale he's talking about, and in Hessdalen, they're sometimes as big as a house, the ball lightning, and maybe even bigger, like tens of meters across in some cases. But is that just glow over a field area, and actually the ball lightning is very tight? Well, that's a question for another day. But what's come out of this is the intensity and the difference. There are a lot of ones which are not much more than a hot particle. Then there are ones that have extreme levels of both forward projecting magnetic beam and magnetic field, which is highly localized, that you're seeing here. That it doesn't really get affected and then it immediately gets affected. There's like it's a non-linear field. It's incredibly intense. And then it's irresistible, in fact. And the fact that these things do like to join together and merge together, we've seen this with all the videos that I've shared of Henk, yourself, where they can blend into each other. and merge that way. You're seeing another way where they can join and mesh together. Now you can imagine in a cavity or in some other sort of confining space, these meshings would want to go on. They would want to join, and then if the loop, there's some sort of magnetic joining between the north and south, or even the weak north and the strong south, or weak south and the strong north, you get some sort of chain building up. Then you can end up with these aggregates that can, as I say, they form all of the allotropes of carbon, and I will talk about this in another presentation. Yes, we can produce EVOs from our fingertips. In fact, everything which is a spark can produce EVOs. No, you can't source a Mars gas. He will sell you a device if he likes you for about $45,000. But I think with the understanding that's coming out of this work and other work, these things will become clearer as to what is actually going on. But the Mars gas is creating a dense matter. And so is Brown's gas, and it's to do with the relationship between exotic vacuum objects that are synthesized in the cavitation bubbles, and the oxygen. What if the sea people are currently at war with the powers to be, and that's why we're in lockdown? Who knows? Maybe. Is the EVO a black hole? I would suggest it's a black donut. What you're seeing here is we've seen event horizons. I think the best example is that 2006 interview, which I have in my Sochi presentation from 2018, by S.V. Adamenko. It's able to capture matter. Now, if you look at the model that is preferred by Bogdanovich for the type of pseudo-magnetic monopole, you will get a unification of forces, and in there you will get basically not only bosonic, a cluster of bosons, which can just occupy the same space-time over and over again. You might even get a level below that where you are losing identity of even the nucleons, and you're just getting like what Schrödinger's called a quark soup. It's a shame we can't see dark mode interactions going on here. I think you can. I think if you see some random movements in these traces, and you can spend a bit of time with them when they're published, I think you can safely say that if something suddenly, for no obvious reason, seems to have a complete change of direction, or seems to orbit around something, I would suggest that there is dark mode EVO in play. Anything's possible, Gardy. Stanley Meyer's work will be using this. It will be producing exotic vacuum objects, coherent matter, in the cavitation. And when you have electrolysis, you're going to get cavitation as well, and also buckets of electrons to help. Do you have a list of supplies so I can help replicate and scale up this experiment? We are going to Hank's shared his circuit diagram and basic overalls. Dave is working on that. We do ask that people are aware of the risks, and they make available to us, a video saying, I know the risks and I could kill myself, and this is my choice and I'm taking it onto myself. So, we're at the point, I think, that with a bit of work, this is already replicatable both between parties, and in the case of Dave, many subsequent experiments. Intermesh threads of nature in the universe. What makes the Evo tract glow? From Axel. I believe, basically, Ken Shoulders says, as it is basically consuming matter in excited state, it outputs, sometimes sheds electrons, but it also outputs mostly 2 kiloelectron volt photon, 2 kiloelectron volt photons. Is it photons? Oh, I'm getting tired now. 2 nights without sleep. Yeah, and so 2 kiloelectron volt X-rays, soft X-rays, and so these will excite gases around them, ionize them, and produce a glow. So they're eating material and causing a glow around them as they go. It's well described by Ken Shoulders. Yes, yes, Bob, we can only see the result of the dark mode on the particles of plasma. Yeah, that's it. If you want to see a dark mode Evo, you've got to make it a white mode, and then it's not a dark mode. But a dark mode can go through things, and it can still influence things. And so, there we go. We don't see the cause that would be helpful in understanding this better. The cause of what you're seeing here is self-organization. It's matter doing what it wants to do. Under these circumstances, the matter is doing the thing it most wants to do, which is organize these wacky structures and wacky arrangements of things. Okay. Do the diameter of the tracks reflect the power of the Evo? Yes and no. They seem to have quantization, okay? So, it might be the state that they're in, but certainly in this sequence of video here, the one that we follow through its journey here, it's already highly energetic. And so one way you can tell the energy is the distance it travels. The next thing that you can tell its energy is the thickness, because that might not change the actual amount of diameter of the core structure, but it's certainly causing a larger area to be ionized or influenced, either ions or electrons around it. And if we step forward, it then hits the cathode here and gets incredibly energized and bright. It's even brighter here, so it's brighter here after it's hit the cathode again, and then it jumps and hits the cathode again, and it gets so much energy. It's like, you know, if you were to change the exposure, if it was possible even more on there, I would imagine that this would be one of the brightest things in the entire field of view. And then it goes around, it's still bright, it's not losing, it's just so bright. And then this one comes in, which is obviously much less energetic, but it starts to immediately become in phase, getting into phase, and then it's in phase with it. And I imagine there is some extremely high speed, electronic speed sharing of energy between these two. And then this one comes in and loops itself around, and then they all come out at roughly the same dimension. So it's like, this is fat, this one becomes fatter, the combination is fatter than it was originally. They may be like sitting alongside each other, but this one comes in, and then by the time it's gone and interacted with that one, they've all kind of like divvied up the energy. But as you move forward, the original one is still higher energy than the one that come out, and then this is the one that influences this, and then the track becomes interacting with it. It kind of, if you imagine got the question is the glow a small electron avalanche? Yeah, effectively you've got something that's highly negative, and it's
throwing out 2 kiloelectron volt soft X-rays, and that is ionizing matter around it, and then those electrons might be at fairly high enough energy themselves to cause further ionization. And so yes, it's kind of like an ionization around it. Is ether intelligent life? I think all consciousness works through the ether. Do you have a possibility? A not very good magnet has been tested in one of these, in some of these experiments, and I'm going to go through those videos and look at the interactions. There are some interactions, but in the next series of of experiments, Dave's going to put a much more powerful magnet in there. The problem is with these neodymium magnets, if they get to 70 degrees or so, they start to lose their magnetism. So you have a small window. Fortunately, the experiments are short, and so we should have an idea. The other thing is to have a field in there, but there's so many fields going on, both between the EVOs themselves and the cathode and the anode. I imagine actually the fields from the EVOs are probably far more intense than the field between the anode and cathode. So I guess the question is, no, we don't have a way to necessarily measure the magnetic field in there. I think what you're looking at are 1/60th of a second frames, and there's a lot of changing of the fields in there because these things have got their own fields. I think it would be very difficult to get a magnetic field picture of what's going on, because you're not only you're looking down into the plasma. I'm looking at part of the frame here, and you're looking through the overall plasma. I think it's just going to be very difficult, but it's a good thing to hold in mind. Not talking about CRISPR here, but certainly makes helixes. Okay, the ether may be conscious on its own. Yes, possibly. How do neutrinos interact with magnetic monopoles? Well, Shoulders evolved from just talking about electrons being the structures to electrons and ions, i.e. charge clusters, to being exotic vacuum objects, recognizing that there's a whole smorgasbord of things going on. From the outset, Takaaki Matsumoto said that the confining structures are made of positrons, electrons, and neutrinos, and that the ions are captured within that. The neutrinos, some type of neutrinos are said to have a magnetic field. If the overall structure has a magnetic field, that might be because of a large number of cold neutrinos in there. Not neutrinos, cold neutrinos. Not neutrinos, like infrared light, gamma rays. We're talking, normal neutrinos are gamma rays like, and cold neutrinos are like infrared light. They're very, very different things. And I talked in the previous presentation about how neutrinos and electrons can share energy. This needs to make it to colleges of academic community too. I know they're sensitive. The thing is about these videos, they just are what they are, and you can say this can't possibly happen, but it's happening. Yeah, but my science book says it can't happen. It's happening. Maybe they are the magnetic monopoles. Yes, David. Acoustics definitely involved and probably quite important to the initial self-organization. I mean, the whole universe is vibration, isn't it? Shockwave. I'm not talking about relativistic neutrinos. I'm not talking about relativistic neutrinos. If you want to know about what type of neutrinos I'm talking about ones that 30 years of research established in here. You're not going to understand the type of neutrinos unless you at least go and read his published papers. That's Alexander Parkhomov. You're just not going to understand it. So, and you're not going to find it on Wikipedia either, or most of the web. Slobodan, that might be an idea, yeah. Actually, you know what? I think you're a perfect candidate for replicating this work, and if you're interested, then maybe we can help facilitate that. They seem to. It might be that if you can imagine those mushrooms as magnetic monopoles, yeah. So let's say we've seen these kind of birdie structures, but they're actually sliced through like a mushroom, and they have north and south variants. And this was proved by the Moscow Physical Nuclear Research University by Bogdanovich. If they are traveling along their own magnetic field and just spinning, they produce a straight line. But you can imagine that if there was a high energy knock to one side, they might wobble. They might wobble like this, and they're still following their own magnetic beam, but the magnetic beam is shifting in front of them, so they're kind of following it. So, you know, depending on how it's formed, it might the explosive release of it from a superstructure, you might end up with just a side-to-side wobble, or you might end up with kind of spinning top wobble, which gives you a helical path, and so forth. So that's kind of how I imagine these. One way that they could explain the individual paths that these take. If you get another, Gordon, if you get enough filaments wrapping around, is it possible to create a plasmoid? Lutz Yatner and many other people would say all of these are plasmoids, but plasmoids are supposedly just ion and electron pair clusters. That is, it's not quite a plasma. You have a relationship between the ion on the electron, and then these form clusters. This isn't sufficient, and in fact, Takaaki Matsumoto said, I think in 2001 in fusion technology, plasmoid is not a sufficient description for what he calls the NATO model, but these itonic clusters. And I think that Ken Shoulders would agree with that, and I think I would agree with that. The term plasmoid and condensed plasmoid is an artifact from the first person that researched that. But I think John Hutchison's work and the review of that with the work of Bosick through Ken Shoulders, really with Matsumoto's work and Roitskev work, they kind of really defined that there's more going on than just ion-electron pair clusters. Yeah, LLP's reactor will be making similar structures, self-organizing structures. That's their whole point. They still carry the normal name, plasmoids. Bistoic, I would really counsel against doing Leclerc's. It's the fast way to the grave, to be honest. The emissions from cavitating devices such as Leclerc's and hydrosonic pump type heat generators, they produce nasty levels of intensity of strange radiation. I don't read books, but I did translate one and lay it out and get it published. But I read a lot of papers, and I like studying visual things. Guardia, are you a question generator tonight? Okay. Okay. Zabadan, did you have contact with Lutz? Yes, I've met Lutz. Yes, I met Lutz before ICCF 22. Yeah, he has a lot of theories about condensed plasmoids, and I actually shared some of his paper in this discussion. However, you are physically seeing in these VEGA videos from Henk and David and the analysis of them, you are actually seeing what these things do. We're seeing what they do. He's been working from the aftermath of the witness and trying to, which many people have done, to work back. I believe what you're seeing here is the actual video of these things coming together, how they break up, and so on. And this is more akin to what Ken Shoulders was doing. Yeah, welding will give you cancer, and probably because it's making a lot of exotic vacuum objects. Okay, BP, I'm glad that you saw the diamonds and that's it. Good, excellent. Thanks for answering the question, Axel. Yes, there will be radiation from pulsed DC into water. Yes, that is exactly what, when I was sharing the work of Zhigalov, which I have here, if I go to it, this was produced by a induction coil field collapse discharge into this electrode onto this plate in water, and this produced the strange radiation tracks that are here, which transmuted elements, and this strange radiation track here. So yes, you will be producing radiation. Okay, so I think it's 11:45 here, so I've got to sneak past the police again. So thank you very much for your time, and thanks again to Hank and David for being a pleasure to work with. And I think this can really, these particular videos are demystifying for me what I've witnessed with the forms of strange radiation track that have been observed by many authors over many years. And I think we're getting to the bottom of this, and I will say this: I believe that this technology will allow everything that Ken Shoulders said it would allow. this is disruption of material, propulsion at any point in the universe, it will allow transmutation. And that is, I say that this is the basis of alchemy. I am saying that this probably has been weaponized, which is just terribly sad, but it can be the basis for, in my view, what I hold dear is for radiation remediation, both to deal with the 75 plus years or whatever of nuclear waste that's piling up, and also to make it possible for small communities to have a very small nuclear reactor that would fail safe, and that if you needed to clean it up, you could go and clean it up in 10 minutes or a couple of days, let's say, and it's not a societal threatening event. This enables the uraniums. There's quite a lot of uranium. There's a lot of other things like thorium that could be used, and there's already a fuel cycles that are established, that are known, and that this technology, you can use what it likes to do, which is to make matter into other matter, and it tends to be matter that's compatible with biology. Itself, in doing that, can damage biology, but if you did that in a controlled way, then I believe you can use it for that purpose. And also transmuting matter in places where it's not available. So if you go to a planet and it has only a lot of silicon and stuff, and you want to make all the elements for life, this technology can do that, and also the ability to get there and to shield yourself from all kinds of threats along the way. So there are very, very many things that this can do, and when you understand and you can see, if you look at what I've shared with you tonight, I think it becomes obvious if you just spend a bit of time thinking about the actual reality of what is going on in those videos. It is showing you and telling you some amazing, amazing things. So with that, thank you very much for your time, and I will say good night.